Math and Beats. This video is all about introducing L'Hospitals Rule. What is this L'Hospitals Rule? Well, we're going to get to it, but first we're going to consider a couple of things here. Alright, now first, let's just recall something. Properties of limits. Assuming we have two limits, say limit as x goes to a of f of x, and a limit as x goes to a of g of x, and they both exist. Then, the quotient limit law says, if I take the limit as x goes to a of the quotient f of x divided by g of x, that is the same as the limit as x goes to a of f of x divided by the limit as x goes to a of g of x, provided that the limit as x goes to a of g of x is non-zero. So that's an already previously established limit law. So somehow that's relevant. Consider this particular limit right here. The limit as x goes to 0 of 2 times sine of x divided by 3 times x. Notice, as x goes to 0, both the numerator, 2 times the sine of x, goes to 0, and the denominator, 3 times x, goes to 0. And so because of this, it follows that the quotient limit law cannot be used in a particular situation like so. And moreover, that quotient, 2 times sine of x over 3 of x, goes to the form 0 over 0. So what to do with that? Well, we have also already previously established that the limit as x goes to 0 of sine of x divided by x is actually equal to 1. And thus, using that result, we can say that the limit as x goes to 0 of 2 times sine of x over 3 of x should be 2/3, since you could just pull out this 2/3 out in front, and you're left with 2/3 times 1. So the limit does exist, even though the original form had this form of going to 0 divided by 0. Moreover, let's consider another situation. Consider this limit right here. The limit as x goes to 0 from the right of the negative natural log of x divided by the cosecant of x. In this situation, notice that as x approaches 0 from the right, negative ln of x is going to approach infinity, and cosecant of x also approaches infinity. And in this situation, it follows that the quotient, negative ln of x divided by cosecant of x, as x approaches 0 from the right, approaches this form infinity over infinity. And unfortunately, that's not necessarily going to be equal to 1, since infinity is not a numerical value. However, given the graph of this function, negative ln of x divided by cosecant of x, that we're about to see below, it's going to seem to indicate that the limit actually does exist and is equal to 0. So, taking a look at the graph, here it is. Here is the graph of y is negative ln of x divided by the cosecant of x. And as we can see, as x is approaching 0 from the right here, right, the function seems to be getting closer and closer to 0. Now, by all means, this isn't necessarily proof that the limit is equal to 0, but it seems to indicate that. And so we have these two different kind of obscure forms of limits that we've seen thus far in this video, in which we can't apply limit laws, and yet the limits seem to exist. At least one of them seems to exist. The first one definitely existed. Both of these forms that we see are called indeterminate forms. So this is a big word right here that has to do with the rule eventually called L'Hospitals Rule. Indeterminate forms. And these forms being 0 over 0 or plus or minus infinity over infinity. So we just saw two different examples of one of each of these. So like I said, these two forms right here are the indeterminate forms of concern. Indeterminate, kind of think of as not determined. if you will. There's other stuff going on that we have to figure out. And we can see also by the previous two examples that limits which have this form can definitely exist. Now, we're not claiming that they always exist, but we just saw a couple that, well, they can exist, right? The limits, if they have this form. So the question is how to deal with such limits. Now, you go back to when you first talked about finding limits and the attempt in which we could apply algebraic methods, right? We could attempt algebraic methods to find such limits, or maybe some more obscure methods, but that's not always going to be possible. For instance, this limit right here that we looked at earlier, the limit as x goes to 0 from the right of negative ln of x divided by cosecant of x, it is not very apparent what type of algebraic manipulations we might need to perform on the function that we're taking the limit of in order to manipulate it into a form for which we could then evaluate the limit. Sometimes it's very convenient to use algebraic methods like factoring or rationalizing or simplifying, right? But in this case, something like this limit that we see, what would we even start with? So here is where our rule comes into place and is very useful. L'Hôpital's Rule, as we say, which is named after a 17th century mathematician by the name of Guillaume de L'Hôpital. It states that if given a limit of the form, like the ones we've been seeing right here, the limit as x goes to some particular location A, of a quotient of two functions, f of x divided by g of x, if you have such a type of limit. And one of two things happens. Either the limit as x goes to a of f of x and the limit as x goes to a of g of x are both 0. So in this case, you'd get that 0 over 0 indeterminate form. Or if you have the limit as x goes to a of f of x and the limit as x goes to a of g of x are both some form of infinity, so either infinity or over infinity, like we saw earlier, or even negative infinity over infinity. Either one of those. If it has one of these two types of indeterminate forms, then the theorem says, the rule that was established, is that the limit as x goes to a of f of x divided by g of x is actually the same as the limit as x goes to a of f prime of x divided by g prime of x. So think about what that really means. The limit of a quotient of two functions, so the quotients of their outputs, is actually the same as the limit of the quotients of their slopes at the same location, in this case as x goes to a. Now that is not trivial. However, we can go ahead and prove one of the forms here to verify that it indeed is true, at least for one of the indeterminate forms. So let's take a look at that first proof, the proof of the 0 over 0 indeterminate form case here. Okay, so for this particular quick proof that we're going to look at, suppose that f of x and g of x are both continuous and differentiable at the location of x is equal to a, and assume f of a and g of a are both 0. So because we're continuous, of course, the limit as x goes to a of f of x and the limit as x goes to a of g of x will be equal to f of a and g of a respectively. And in this case, we're assuming they're 0, and both of these functions are also differentiable at a, and we should probably say nearby a as well, along some open interval. Then, if you go ahead and just take a look at this limit as x goes to a of f of x divided by g of x, well, if I just go ahead and subtract 0 in the numerator and denominator, I've changed nothing. So it's actually the same as limit as x goes to a of f of x minus 0 divided by g of x minus 0. But f of a and g of a are both assumed to be 0. So this limit is the same as the limit as x goes to a of f of x minus f of a divided by g of x minus g of a. If I go ahead and just multiply the numerator and denominator there by 1 divided by x minus a, keeping in mind that this is not true at x is equal to a, but we're taking the limit as x approaches a, so that's all good. Then I can rewrite this as this form. The limit as x goes to a of f of x minus f of a divided by x minus a, all divided by g of x minus g of a over x minus a, which is the same as the limit as x goes to a, right down here, of f of x minus f of a divided by x minus a, over the limit as x goes to a of g of x minus g of a divided by x minus a. But by definition of each of this numerator and denominator here, the numerator, by definition, that's the derivative of f at a by definition, and correspondingly the denominator is the same exact thing as g prime of a, the derivative of g at a. And of course, that is the same thing as the limit as x goes to a of f prime of x divided by g prime of x. Because they're both differentiable, then of course, as x goes to a here, this function in the numerator approaches f prime of a, and the denominator approaches also g prime of a. And so what we start with right over here, what we end with right over here, this proves the special case for which we have nice continuous and differentiable functions, and we are starting with the indeterminate form of 0 over 0 in our limit. Now, this does not prove the plus or minus infinity over infinity indeterminate form. That's a much more advanced proof that requires some real analysis. So if you're interested in seeing that, go search it up on the internet. I'm sure you can find a proof of it, and you will find, indeed, it is also true. So it's not just some made-up thing. It does work. It is an established theorem and rule. And to conclude this video, we're going to just revisit that same limit that we saw earlier, right? The limit as x goes to 0 of 2 times the sine of x divided by 3 of x. Now, we already know that this is equal to 2/3, and that's because we know the limit as x goes to 0 of sine of x over x is equal to 1. But even establishing that, it requires a lot of work. And so here, instead, we'd like to see a quick example of how to use L'Hopital's rule to find the limite. Haha, no e there, right? Just the limit. So how to approach this? Well, notice, let's just start with the limit. The limit as x approaches 0 of 2 times the sine of x over 3 times x. Notice that in the numerator, as x approaches 0, 2 sine of x approaches 0. And in the denominator, as x approaches 0, 3 times x also approaches 0. And so we have this situation in which, first of all, we have an indeterminate form. In this case, 0 over 0. Part of the condition of using L'Hopital's rule is starting with one of the two indeterminate forms. Moreover, both sine of x and x are differentiable functions for all real x, really. So 2 times sine of x and 3 times x also differentiable, and moreover continuous for all real values of x. So L'Hopital's rule applies to this situation. And thus, what it says is that this limit as x approaches 0 here of this quotient 2 times the sine of x over 3 times x, that should be the same as the limit as x approaches the same location 0 of the derivative with respect to x of that numerator 2 times sine of x divided by the derivative with respect to x of the denominator. Now, when we write such a thing, it can sometimes be a little misleading when we write such a statement. So oftentimes what we do is when we're applying this L'Hopital step like we're doing right here, we often write some kind of notation in between the steps that helps us understand that we have actually applied a L'Hopital's rule. And so in this case, using an H seems to be a nice way of denoting this, to denote, oh, we have used the L'Hopital's rule at this step, in that we are going to differentiate the numerator with respect to the input variable and also differentiate the denominator with respect to the input variable. Moreover, even furthermore, Notice this is not a quotient rule here, right? We're not applying the derivative of a quotient. Rather, it is the quotient of the derivatives as per the rule says. So I got to differentiate both the numerator and denominator here to produce the new limit for which we are going to find. So let's do that. All right, this is going to be the limit as x goes to 0 of numerator there, differentiate 2 sine x with respect to x, give us a 2 times cosine of x. And clearly the denominator has a derivative of just 3. And so now we can actually evaluate this limit because, of course, cosine of 0 is 1. You get 2 times 1 over 3, which indeed is 2/3, like we had already said. So it's just an example here really quickly to show us how the L'Hopital's rule is going to work. And also don't forget this notation when applying the L'Hopital rule step. Just some notation in there saying to the reader that we have applied the L'Hopital's rule. I like to personally use that H notation, but it's not unique. So that's it for this video. This video was just supposed to kind of get us motivated in looking at certain types of limits that have these indeterminate forms, and then establishing L'Hopital's rule of how to approach such limits, and finally, a very quick example to get us going here. Upcoming videos, we're going to look a lot more examples, including other various types of indeterminate forms. So that's upcoming after this. Until then, you know what it's math and beats a mountain now.